Right, so Saudi Arabia is building a 1 kilometre tall skyscraper on the coast of the Red Sea. Not 900 metres, not 950, 1 full kilometre. A number so round it sounds made up. For 6 years it stood completely still, abandoned. A 63-storey concrete skeleton baking in the Saudi sun, going nowhere, while the rest of the world quietly assumed the whole thing was finished. It wasn't. This is the Jeddah Tower. The world's first megatall building, the structure that will make the Burj Khalifa look like a warm-up act. 167 habitable floors. A cantilevered outdoor terrace at 630 metres. An elevator ride so long they had to reinvent the rope. Total cost, $1.2 billion, just for the tower. The surrounding city it anchors, $20 billion, and the engineering problems it had to solve. Frankly, unreasonable. The impossible problem. Here's the thing about building the world's tallest structure. Every generation thinks it's already been done. In 1931, the Empire State Building went up. Done. Limit reached. Then in 1973, the World Trade Center. Then the Sears Tower. Then the Petronas Towers. Then the Burj Khalifa in 2010 at 828 meters. And everyone agreed, that's it. That's the ceiling. You cannot go higher than that. Saudi Arabia disagreed. The Jeddah Tower was announced in 2011 as the centerpiece of Jeddah Economic City, a brand new urban development on 5 square kilometers of waterfront land, 20 kilometers north of the city. The target height was exactly 1 kilometer, a psychological statement as much as an engineering one. The designer, Adrian Smith, the same man who drew the Burj Khalifa, he knew precisely how far the previous record could be pushed because he'd set it. But a kilometre isn't just a taller building. It's a fundamentally different category of problem. At 828 metres, the Burj Khalifa enters the atmospheric boundary layer, the zone where wind is shaped by the terrain below. Trees, buildings, hills, they all create turbulence that engineers can model and design around. At 1 kilometre, you're above most of that. You're in cleaner, faster, less predictable wind. The kind that doesn't care about your computer models. So Smith gave the tower 3 tapered petals, a Y-shaped footprint that looks from above like a desert plant pushing up through sand. It's not decorative. Each wing terminates at a different height, which means the wind never locks onto a single rhythm. It can't organize a vortex. It gets confused and moves on. Wind tunnel tests at 1 to 600 scale proved it works. At the highest occupied floor, 654 meters, the peak movement during a 1-year wind event is 7 milli-G. The human comfort threshold is 12. The building barely registers the wind, which, when you're sitting in your office 2/3 of a kilometre above the ground, is presumably quite reassuring. Then there's the Spear, the uninhabited top section, where the engineering gets properly strange. The upper structure required a 2-stage tuned mass damper system. An 870-ton primary mass at level 206 and a 260-ton secondary mass at level 218. 2 enormous pendulum-like counterweights suspended near the top of the building, swinging in opposition to the sway. The ocean liner has stabilizers. The kilometre-high skyscraper has 1,130 tons of dead weight, doing slow, deliberate physics at 874 meters above sea level. Now, the foundation. This building weighs over 900,000 tons. That is, for reference, roughly the same as 7,500 fully loaded Boeing 747s, standing on a single patch of coastal Saudi Arabia. The soil near the Red Sea is weak. The water table is high. The ground is saturated with salt water, which doesn't just sit there politely, but actively eats concrete from the inside out. You cannot simply put 900,000 tons on that and wish it well. So they drilled 270 piles into the earth, each one 1.5 to 1.8 meters in diameter, each one driven up to 110 meters deep, deeper than a 35-story building is tall, to find stable rock. Then they poured a concrete raft on top, 5 meters thick, covering 7,500 square meters, approximately 1 football pitch. Specially formulated concrete, low permeability, resistant to saltwater intrusion. And before any of that, engineers spent months pumping down the local water table, manufacturing dry land out of wet coastal ground, purely to make the pour possible. That was the foundation. Construction hadn't started yet. The project that died and came back. Construction began on April 1st, 2013. The Saudi Bin Laden Group, one of the largest contractors in the Middle East, moved onto the site. By 2017, they'd reached 63 floors. The thing was rising. One of the world's greatest buildings was apparently happening. Then, in January 2018, it stopped. In November 2017, Crown Prince Mohammed bin Salman launched an anti-corruption campaign. Several hundred Saudi businessmen and officials were detained at the Ritz-Carlton Hotel in Riyadh. Among them, key figures connected to the Jeddah Tower project. The Saudi Bin Laden Group took a severe financial hit. Cash flow collapsed. Workers weren't paid. Many left the country. Then COVID arrived, a global pandemic, on top of a financial crisis, on top of a political earthquake. For 6 years, the Jeddah Tower stood as a half-finished concrete monolith. 63 floors of ambition, going nowhere. International press wrote its obituary with some enthusiasm. The same critics who'd called a kilometre-high building impossible now called it unnecessary, delusional, and almost certainly abandoned. That's the point at which you want to subscribe, by the way, because what happened next is the part that doesn't make rational sense. In late 2024, Saudi Arabia rehired the Saudi Bin Laden Group. New contract, 7.2 billion Saudi riyals, roughly $2 billion US, to complete the remaining works. Full operations resumed in January 2025. As of early 2026, the tower has passed 80 floors. The construction pace, 1 new floor every 3 to 4 days. Projected completion, August 2028. The project everyone buried is now the fastest rising megatall structure in history. The engineering that didn't exist before. Getting 500,000 cubic meters of concrete to the top of a 1-kilometer building is not a logistics problem. It's a physics problem that didn't have a solution because no one had ever needed one. The Jeddah Tower uses 4 Schwing SP 8800D stationary pumps, each one powered by a 440 kilowatt diesel engine, roughly 7 Formula One cars dedicated entirely to pushing concrete upward. Maximum pressure, 243 bar. That's approximately the pressure at 2,430 meters underwater. But there was a catch. No one had ever pumped concrete to 1,000 meters before. Theoretical models exist, but at this scale they produce numbers engineers don't entirely trust. So before building anything, they ran real-world trials, adjusting viscosity, water content, and setting time until the mix stayed fluid all the way up, and solid the moment it arrived. Then there's the heat. In Saudi Arabia, concrete poured in direct sun can hydrate too quickly. Rapid hydration means cracking. Cracking in a structural wall at 600 meters is not a maintenance issue, it's a catastrophe waiting for a date. Their solution: replace part of the mixing water with flake ice. Pulverized ice added directly to the mix, keeping the temperature below 25 degrees Celsius during transport and placement. Major pours are conducted at night, when the desert actually cools down. You are pumping refrigerated concrete a kilometer into the sky. At night, in Saudi Arabia. This is normal now. Then the elevators. The observation deck sits at 630 meters, a 30-meter cantilevered platform that was originally designed as a helipad, until someone pointed out that landing a helicopter at 630 meters in unpredictable high-altitude winds against a glass facade was perhaps not the wisest operational decision. It became a terrace instead, arguably more useful. Getting people there requires rethinking one of the most basic components of any tall building. Standard elevator technology has a hard limit of around 500 meters. The reason is embarrassingly simple: steel cable. A steel hoisting rope long enough to span 500 meters weighs so much it can barely support its own weight, let alone a car full of tourists. Beyond that distance, passengers have to transfer between elevator banks, which defeats the point of a single, soaring ride to the world's highest observation deck. KONE, the Finnish elevator company, solved this with UltraRope, a carbon fibre core surrounded by high-friction plastic coating. It weighs 1/5 as much as steel rope of equivalent strength. For an 800-metre run, it uses 40% less energy. The counterweights are smaller, the motors are smaller. The whole system becomes lighter as the building gets taller, which is precisely backwards from how steel behaves, and precisely what you need. There's also the sway problem. Tall buildings move. In strong winds, steel elevator cables vibrate against shaft walls, resonating at frequencies that force systems to shut down entirely. UltraRope resonates at a different frequency altogether. The building sways. The rope doesn't care. The elevators keep running. The tower will have 59 elevators and 8 escalators, total 67 vertical mobility units. The observation deck shuttles are double-deck units, 2 cabs stacked in a single shaft. They travel at 10 meters per second. They include pressure control systems to prevent the rapid altitude change from causing nausea. You board a lift in the lobby and arrive at 630 meters in under 2 minutes. Ears intact. The cranes lifting all this material are not ordinary cranes either. The site uses Favco M390D and M390DS diesel hydraulic units. Safe working load, 32 tons. Maximum hoist speed at light load, 232 meters per minute. And crucially, they climb. An internal hydraulic system allows each crane to move upward through the building's central core as each new floor is completed. The building rises. The cranes rise with it. They run entirely on diesel, with no connection to the local power grid. If the grid fails, the cranes keep lifting. The bottom line. So here we are, the Jeddah Tower, 900,000 tons of concrete and steel, sitting on 270 piles, driven 110 meters into the Saudi earth, rising on refrigerated concrete pumped to heights no one had managed before, served by elevators running on carbon fibre rope that didn't exist a decade ago. It is also the anchor of a $20 billion city, hospitals, universities, a Four Seasons hotel, a planned metro system, housing for 100,000 people. Saudi Arabia's physical argument that Vision 2030 is real, that an economy built on oil can become something else entirely. When the Burj Khalifa opened in 2010, it did exactly what Dubai claimed it would. It transformed a sandbank into a global city. Property prices in downtown Dubai tripled within a decade. Tourism exploded. Entire industries relocated. If the Jeddah Tower does the same thing, and the $20 billion surrounding it suggests someone believes it will, Saudi Arabia doesn't just get a building, it gets a new economic engine on the Red Sea coast. And the Burj Khalifa, the building that was supposed to be the permanent limit. The Jeddah Tower will clear it by at least 173 meters. They said a kilometer was structurally impossible. Then they said the project was financially finished. Then they said 6 years of abandonment had killed it for good. They were wrong all 3 times. The question isn't whether it gets built. It's already happening. A floor every 3 to 4 days. Concrete pumped through the Saudi night. Cranes climbing their own building toward a height that has no precedent. The question is, what comes after? China is already studying towers that could challenge Jeddah's record. The UAE is reportedly evaluating a 1.5 kilometer concept. Once you prove a kilometer is possible, someone immediately starts asking about 2. That's not engineering ambition, that's just how this works. What project should we cover next? Drop it in the comments and don't forget to subscribe.